Okay, Chemistry 111. This is where we left off last time in Chapter 9. So we were taking a look at Chapter 9, which deals with chemical bonding, the basic concepts of chemical bonding. So last class we took a lot of time and we talked about ionic bonds, and then we got into covalent bonds, and we got into Lewis structures after we had reviewed, or after we had gone over the concept of Lewis dot structures. Well, I want to just get you to think about for a second, what if you had to draw the Lewis dot structure of ozone, right? Ozone that is found, of course, in the ozone layer is a gas. In last class, I talked to you a little bit about what a ozonizer is and how you can use an ozonizer to remove odors from a home or an automobile or something like that. Anyhow, what if we tried to draw a Lewis structure for ozone? Well, in the interest of time, I'm just going to show you what a reasonable Lewis structure for an ozone molecule would be that I have in this black box here. Now, if I label those atoms just for fun, if I call them A, B, and C, somebody else might draw another resonance structure where they have the negative charge on B and they have, sorry, the negative charge on A rather, and then they have a neutral atom for C. And so both of these Lewis structures are perfectly acceptable. There is nothing wrong with either of these Lewis structures. However, it shows us a limitation with Lewis structure, doesn't it? It shows us that we could run into a situation like the situation that we have here with ozone, where one Lewis structure is not adequate to actually describe the molecule. And so these two molecules that you have shown here, or these two structures, I should have said, these two structures are called resonance structures. It says here that a resonance structure is one of two or more Lewis structures for a single molecule that can't be represented by only one Lewis structure. So we run into many molecules that we can simply not represent just with one Lewis structure. We have to draw two or more resonance structures. Now for ozone, these two are the only resonance structures that we require here. Now, if you're wondering, well, how do you know that the molecule isn't vibrating back and forth here between the two? You see this arrow here? This is called a resonance arrow. So it's important that you understand that the molecule is not vibrating. It's not this one second, and then all of a second it's this one the next second. What the Lewis structures or the resonance structures tell us is that, in fact, the structure of ozone is really a hybrid of these two. Okay, if we could put these two and blend them together, we would actually have the correct Lewis structure, or the overall resonance, or the overall structure. And you can represent that. It's called a resonance hybrid. However, we don't cover that in our class. But one more interesting bit of information that I want to share with you is this. If you look at this resonance structure over here, here we have a double bond and here we have a single bond. Well, based off of what I taught you in the last lecture, this double bond should be shorter, right? It should be shorter than the single bond that's between B and C. But in fact, that is not the case. In fact, the bond lengths for both of these bonds are identical. They are 128 picometers. What does that tell you? That tells you that, again, there is no double bond in the overall structure, or the structure of ozone, right? It's a hybrid between the two. Let me prove it to you. If you look at an electrostatic potential map of ozone, you see that the electron density is actually spread evenly throughout the molecule. You see that there's some red density over here, but you see you have the exact same amount of red coloring here. That means that the negative charge on the terminal oxygens here is evenly spread throughout. And that's what a resonance structure is. And again, there are many examples in chemistry where we have to use resonance structures. We don't always have to use resonance structures, but oftentimes we do. Let me show you an example. This is example question, or example rather, 9.8, comes straight out of your textbook. It simply says, draw three, it tells you three resonance structures for the molecule nitrous oxide, which is laughing gas. And it tells you that the atomic arrangement is N followed by another nitrogen followed by an oxygen. Then it asks you to indicate the formal charge. Then it asks you to rank them in order of their relative importance to the overall molecule. Well, I'm going to show you how to do that. Bud, it's teaching a class right now.
Every part I went on, my parent on the thing of it.
Okay, I'll come take a look at it in a second, okay? Don't worry about it. But Dad's teaching a class. Can you go upstairs, bud? Yeah. Okay. All right, and I'm going to show you through this example how to evaluate resonance structures in terms of their relative importance, because this is something that you have to know how to do. So let me show you, and again, in the interest of time, I'm just going to kind of go over the structures quickly. In our textbook, there's a full treatment of this problem, of course. So we need to have nitrogen, nitrogen, oxygen for the first one. I'll draw the resonance arrow. Then we have a second resonance structure. Then we have a third resonance structure. Well, how many total electrons do we have in dinitrogen oxide or nitrous oxide, which again is laughing gas? Well, we have 5 valence electrons for nitrogen. There's 2 of those, plus we have 6 from oxygen. So that gives us a total of 16 valence electrons. Well, so far in this Lewis structure, I've only used up 4 valence electrons, haven't I? If I complete the octet on the oxygen like this so that it has a negative charge, and then I complete the octet on the terminal nitrogen like this, then I end up with a positive charge on the nitrogen here. So this is a perfectly legitimate Lewis structure, the one that I have on the far left. Well, what if I was to move one of these pi bonds here and I moved it over between the nitrogen and the oxygen? I can do that, and in that case, I would end up with a Lewis structure that looks like this. Again, I'm going over this kind of quickly just in the interest of time, but I would end up with a Lewis structure here where I have that negative charge moved over onto the nitrogen. And then I can have one more Lewis structure where every atom has a complete octet, where we have a single bond to the nitrogen on the far left. Then we have a positive charge. I'm sorry, didn't want to put that in yet. But anyhow, we have a triple bond to our oxygen like this, and we have a lone pair. Well, if you calculate the formal charge on the oxygen, it's +1. On this nitrogen, it's +1. And on this nitrogen on the end, it's -2. Okay? So either way, all of these molecules are neutral, aren't they? But the structure that's the most likely out of all of these is going to be this one here, most likely. The reason why this one is the most likely is because all of the atoms have a complete octet. And the reason why it's most likely is because the negative charge is on most electronegative elements. Okay, because the negative charge is on oxygen, and oxygen has an electronegativity of 3.5, and nitrogen has an electronegativity of 3.0. So these are the relative electronegativities. Now, if I look at the very last one, the one on the far right, this one is going to be the least likely. Least likely. Not only is the negative charge on a less electronegative element, but we always try to avoid multiple charges. So we want to avoid multiple charges on one atom. So that means we're usually not going to have a +2 or a -2 or a +3 or a -3. That's just nuts. So the one in the far left is the most likely. The one in the middle is somewhere in the middle. And the one on the far right is going to be the least likely. So again, the most important Lewis structure will be one in which all the octets are filled. And of course, in all 3 of these Lewis structures, all the octets are filled all the time. But all octets are full, and any negative charge will be on the most electronegative element. The one that's going to be the least likely here will be one where we have the negative charge not only on the less electronegative element, but we also have multiple charges, and we try to avoid -2s and +2s in our Lewis structure. Well, let's look at some exceptions to the octet rule, because we talked about the octet rule last class. And again, if you look at our 3 Lewis structures that we drew today, if you pick any element, or any atom at random, say you pick this nitrogen here, that nitrogen is surrounded by 1, 2, 3, 4, 5, 6, 7, 8, right? It's surrounded by an octet of electrons. So the octet rule was obeyed in all of our Lewis structures in this problem. But there are exceptions to the octet rule. In fact, I alluded to this last lecture, that there are, in fact, very few elements that really abide by the octet rule 100% of the time. The first one you have to know is beryllium. Beryllium is the fourth element in the periodic table. If you write out the electron configuration for beryllium, beryllium is 1s2, 2s2. That means it's only got these two valence electrons. If it's only got two valence electrons, then its Lewis structure is going to look like this. You're going to have beryllium with two unpaired electrons. Well, the number of unpaired electrons represents the number of bonds that the element can form. And so beryllium can only form two bonds. So beryllium, we could put here Be forms two bonds, like that. Beryllium forms two bonds when it's in a compound. Another exception is boron, and you need to know these exceptions. That's why I'm covering them. If you look at the electron configuration of boron, it's 1s2, 2s2, 2p1. That means that boron has 1, 2, 3 valence electrons. If we write out the Lewis dot structure for boron, we have boron, and it's got 3 unpaired electrons. Therefore, boron forms 3 bonds. Okay, and that's another exception that you need to know. For example, let's say you wanted to make boron trifluoride, right? The boron only is surrounded by a total of 6 electrons, right? And it's going to have no charge. Why? Because boron has 3 valence electrons, subtract 3 sticks and 0 dots equals 0, like that. This compound here, BeH2, that's beryllium hydride. And of course, the beryllium in beryllium hydride is going to be 2 valence electrons minus 2 sticks and 0 dots gives you 0. So it's going to have no charge. Some good exceptions to the octet rule. Another interesting exception to the octet rule are odd electron molecules. Well, odd electron molecules result in what are called radicals. So radicals are molecules that possess unpaired electrons, like this one here in NO, nitrogen monoxide, and those are highly reactive. So we'll put here radicals. Radicals are highly reactive. So if you try to draw a Lewis structure for NO, where we put the deficiency of electrons is going to be on the less electronegative element. It's on the nitrogen. So the nitrogen is only surrounded by 1, 2, 3, 4, 5, 6, 7 valence electrons, okay? But if we calculate its formal charge, right, we have 5 valence electrons for nitrogen, subtract 2 sticks and 3 dots equals 0. So it's got no formal charge. However, since it has that unpaired electron, it will be highly reactive. Another example that's covered in our textbook, and I'm not going to go over it in detail, I don't even have space to do it, but another example would be something like nitrogen dioxide, NO2. And NO2 will actually dimerize. It actually combines with another molecule of NO2 to make N2O4 gas. And you can take a look at that in the textbook, but it avoids having a radical because NO2 has an odd number of electrons. And then when you get to N2O4, it avoids having that radical. Again, I just want to point out, I might have forgotten to say here that when you have the molecule NO, it has 11 electrons. And so since you have an odd number of electrons, you end up with an unpaired electron, which again produces that radical, which is highly reactive. Now, an example that's going to come up a heck of a lot more than the first 3 exceptions are the expanded octet. Expanded octets come up a lot. The reason why is because many elements in the periodic table can expand their octet. In fact, oops, just give me 1 second. If you look at any element with the highest principal quantum number being greater than 2, so if you look at anything from the 3rd period and beyond, okay, and another way to phrase this would just be n equals 3 and higher, okay, those elements have the 3d orbitals available to them. Take a look at the example that's shown here. You have sulfur hexafluoride. That's this molecule here, SF6. Well, if we look at the electron configuration of sulfur, we have neon, then we have 3s2, 3p4. Well, if I write out the s electron, or the s orbital, sorry, I have the 3s, then I have 3p orbitals, right? Because there's 3 types of p orbitals. Then I also have the 3d orbitals, 1, 2, 3, 4, 5, that are available to put electrons in. And so since I have a total of 1, 2, 3, 4, 5, 6 valence electrons, I can put them 1, 2, 3, 4, 5, 6, and now I've got 6 unpaired electrons, which enables my sulfur to form a total of 6 bonds in this molecule called sulfur hexafluoride here. Notice that there's still no formal charge in this molecule. Don't believe me? Well, look at the sulfur. Sulfur is in group 6A. It's got 6 valence electrons. Subtract 6 sticks and 0 dots gives me a formal charge of 0. So that is a perfectly legitimate Lewis structure for sulfur hexafluoride, where it has the 6 bonds. So if you ever are questioning, can I expand the octet of this atom? If it's in the 3rd period or below, the answer is yes. Yes, you can. Well, the best way to master Lewis structures, as I told you a lot last class, was to practice them. So with that in mind, I want to take a look at some examples. And again, since we don't have a lot of time in our Tuesday night lectures, I'm going to kind of go through these ones for you, but I expect you to spend some serious time practicing these. The first one is draw the Lewis structure of aluminum triiodide. So if we have aluminum triiodide, the first thing we'll do is we'll tally up the total number of valence electrons. Aluminum is in group 3, so it's got a total of 3 valence electrons. Iodine is a halogen, which is found in group 7A. So we have 7 valence electrons times 3, so that's 21 plus 3, which gives me a total of 24 electrons. Well, something else I want to point out is that if you look at the electron configuration for aluminum, okay, aluminum is element number 13, and its electron configuration is neon 3s2 3p1. Where did we see a configuration like this before, where we had 2s electrons and 1 p electron? Well, if you look just above aluminum in group 3a, what atom do you see there? You see boron. And so aluminum is going to form 3 bonds because it has 3 valence electrons. So aluminum forms 3 bonds. So we can start like this. Aluminum is the least electronegative element between aluminum and iodine. So we have aluminum with 1, 2, 3 bonds to it like this. Remember a little trick that I told you last class is that whenever you have a halogen like fluorine, chlorine, bromine, and iodine, fluorine only ever forms 1 bond and has 3 lone pairs. But the other halogens like iodine, a lot of the time, not all of the time, but a lot of the time will form 1 bond and have 3 lone pairs. So let's try that. If we put iodines at the end of each one of these bonds and then fill up their octets like this, do I have a total of 24 electrons? Well, let's tally them all up. I've got 1, 2, 3, 4, 5, 6, 7, 8. And then I've got 16, 24, right? 8 times 3 is 24. So yes, I have exactly 24 valence electrons. If I try to calculate the formal charge of the iodine, iodine has 7 valence electrons. Subtract 1 stick and 6 dots gives you a formal charge of 0. Aluminum is in group 3A. It's got 3 sticks and 0 dots, which gives you a formal charge of 0. This is a perfect Lewis structure. There's absolutely nothing wrong with it. Now, this is a Lewis structure. This shows you an exception to the octet rule, doesn't it? Absolutely, because aluminum is only going to form 3 bonds because it's in group 3A. I want to try one more example where we see a violation or an exception is what I should say to the octet rule before we move on. I'll just do this quickly on the bottom of this page, and there's not a ton of room. But what if I had, I'll just do it like this. What if you had beryllium fluoride? Well, beryllium is in group 2A. It's got a total of 2 valence electrons, plus fluorine has 7 times 2 fluorines. That's 14 plus 2, which gives me a total of 16 valence electrons. Well, you should remember from a couple slides ago that beryllium only ever forms 2 bonds. So we have beryllium with its 2 bonds, and you should also remember that fluorine always forms 1 bond and has 3 lone pairs. So we put our terminal fluorines here, and we have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. You can see that we used 8 valence electrons on this side. We used 8 valence electrons on that side. 8 plus 8 gives you 16, and there is a good Lewis structure for beryllium fluoride. All right, let's keep moving, and let's look at an example where we see an octet expansion, an expanded octet. says draw the Lewis structure for phosphorus pentafluoride, which would be PF5, in which all 5 atoms are bonded to the central phosphorus atom. So that tells us right away that if all 5 atoms are bonded to the phosphorus, that means that phosphorus is surrounded by a total of 10 electrons, isn't it? Look where phosphorus is in the periodic table. Phosphorus is element number 15. That means it's in the 3rd period, and so phosphorus can, in fact, expand its octet. It has d orbitals available to it for the expansion. Well, let's tally up the total number of valence electrons in phosphorus pentafluoride. So there we go. Let's move this down here. So for phosphorus, phosphorus is in group 5A. We have 5 valence electrons plus 7 valence electrons for fluorine times 5. So that gives us 35 plus 5, which gives us a total of 40 valence electrons. I'm going to start by putting my phosphorus in the middle. It's going to be surrounded by 5 bonds to fluorine. So 1, 2, 3, 4, 5, like this. Well, another trick that I taught you, and I'm repeating this, is that fluorine only ever has 1 bond and 3 lone pairs. No exceptions to that rule, I promise. Okay, and Mr. Dion doesn't like to promise things to people, but I promise there is no exception to that rule. Now I've got my phosphorus pentafluoride. I've got a proposed Lewis structure. It looks good to me because I have used a total of 8 valence electrons here, right, with the 1 bond and 3 lone pairs, and then I have 5 bonds to fluorine. So 8 times 5 is 40. That looks good to me. What else? My phosphorus does have an expanded octet, right? The phosphorus is surrounded by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. But it's okay because phosphorus is in the 3rd period. Also, the formal charge of my phosphorus. Phosphorus has 5 valence electrons. Subtract 5 sticks and 0 dots gives you a formal charge of 0. Therefore, there is nothing at all wrong with this perfectly good Lewis structure. Give me a thumbs up if you follow me on the idea of making a Lewis structure with an expanded octet. Stop me if you have a question about how I tallied up those valence electrons. Okay, good. Thanks, Anthony, and thanks, Branson. The main thing with Lewis structures, really, and you know what I'm going to say, is that you practice them. I promise if you practice, you will become more proficient at them. Let's take a look at the Lewis structure of a polyatomic ion that you would have learned way back in chapters, I think it was in chapter 2, really, where we covered nomenclature quite thoroughly. And you all learned the Lewis structure of sulfate, right? Everybody should know that sulfate is SO4 2-. But they're telling you that in the Lewis structure of sulfate, all 4 oxygens are bound to the central sulfur atom. Well, let's take a look here. We've got SO4 2-. So sulfur has 6 valence electrons plus. Oxygen has 6 valence electrons times 4. That gives me 24 plus 6, which is 30. But then we have a 2- charge. So that means we have to add 2 electrons. So we have a total of 32 valence electrons. Also, since we have a -2 charge or a 2- charge overall for our polyatomic ion, that tells us that we're going to have 2 negative charges in our molecule. Now, based on what I taught you about where the negative charges should go, which atom would preferentially take a negative charge when you're comparing sulfur and oxygen? Which one do you think is going to be happier with the negative charge? Sulfur or oxygen? Absolutely, Anthony. It's oxygen. Why? Because oxygen is the 2nd most electronegative element in the periodic table. Also, sulfur can expand its octet. Okay? Oxygen cannot expand an octet. Why? Because sulfur is in the 3rd period. Oxygen is in the 2nd period. Well, let's take a look. I know that if I put, you know what, let's fill up the octets of the oxygens like this. Okay? Like that, like this, like that. If you were to propose this as a Lewis structure, technically it would be okay to some degree. However, it is not a great Lewis structure. Let me show you why. If you calculate the formal charge of any of these oxygens, you have 6 minus 6 dots and 1 stick. So that gives you -1. Right? So that tells you that each one of these oxygens Okay, every single one of them is -1, -1, -1, -1. That gives you -4. But the charge on the sulfur is 6 minus 4 sticks and 0 dots, which is +2. So the sulfur is +2, and then you're like, hey, if I take -4 and +2, I get -2. Therefore, hot dog, we have a wiener, everything is great. No, not everything is great. The reason why is because we like to avoid having multiple charges like this. And so the way we're going to alleviate that multiple charge is that we're going to take 2 of the oxygens, we'll remove a lone pair on each of them, and we'll replace it with a double bond. So we'll put a double bond here, and we'll put a double bond here. Now I have 2 negative charges, 1 on each of these oxygens down here at the bottom. These 2 oxygens are neutral, and the central atom, my sulfur, is neutral. And so this would be the best Lewis structure for sulfur, or sorry, for the sulfate ion. All right, a little practice on that. Let's try one more where we have a noble gas compound. If you look at the noble gases like helium and neon, for example, there are no known compounds of those elements. However, xenon is in the 5th period and can form bonds to other elements. So let's just go over this one quickly. We have xenon tetrafluoride, which would be XeF4, like this. It says that all 4 fluorines are bonded to the central xenon atom. Well, this one, I don't like to use the word easy in chemistry class, but you know that all the fluorines are going to have 1 bond and 3 lone pairs, aren't they? So let's tally up the total number of valence electrons. We've got xenon tetrafluoride. Xenon has 8 valence electrons plus fluorine, which has 7 times 4. So that gives us 28 plus 8, which gives us 36 valence electrons. So if we put our xenon in the middle, and we have 1, 2, 3, 4 bonds to fluorine. Each fluorine is going to have 1 bond and 3 lone pairs, like that. That means that I've used up 8 valence electrons times 4, right? Since I've got 4 bonds to fluorine. So 8 times 4 is 32. 36. Subtract 32 electrons means I've got 4 electrons left over. Can anybody tell me where they should go? And it's not a trick question. Mr. Dion hates trick questions. Where would those 4 leftover electrons go? We can't just throw them in the trash. That's exactly right, Anthony. They're going to end up on the xenon atom, right on the central atom like this. Why? Because xenon is in the 5th period. It's beyond the 2nd period. It can expand its octet. Let me prove it to you that xenon has no formal charge. Xenon is in group 8A. It's surrounded by 4 sticks and 4 sticks and 4 dots, which gives me a formal charge of 0. Therefore, this is a perfectly legitimate and is the correct Lewis structure for xenon tetrafluoride. And that's how you do it, my friends. Well, let's move on to something else here for a second. And let's end out the chapter talking about, spent a lot of time talking about bonds, didn't we? Okay, we've made all kinds of covalent bonds. Well, I want to talk to you about the amount of energy that it would take to break a covalent bond, right? Because the only reason that atoms form bonds with each other is to make something that's more stable. So if the atoms become stabilized when they form bonds, right, they complete their octets or duets or whatever. If they become more stable, that tells me that if I wanted to break 2 atoms apart, right, let's say I wanted to break H2, right? Everybody that's hearing the sound of my voice could draw the Lewis structure of hydrogen gas, right? H2. It's just like this. But I would have to, if I wanted to break that bond, how much energy would it take? Well, I have it written right here. We call the energy that it takes to break a bond, we call it the bond enthalpy. Okay, bond enthalpy. And the bond enthalpy for H2 gas just happens to be 436.4 kilojoules. What if you had Cl2? Right, Cl2 is just this, right? Chlorine is a a monatomic molecule. But if you want to break that bond between the 2 chlorines, it's going to cost you 242.7. What if you had HCl, right? What if you had hydrogen chloride gas? That's perfectly legitimate. What if you wanted to break that bond? How much energy would it take? It takes 431.9. Let's keep going. What if you had oxygen? The Lewis structure of oxygen shows a double bond between the 2 oxygen atoms, right? It's going to cost you quite a bit of energy because that's a double bond. So yeah, it's going to cost you around 500 kilojoules per mole. And you can see where I'm going with this. If you have nitrogen, well, nitrogen's got a triple bond in it. So if you want to break the bond between two nitrogen atoms, it's going to cost you a hell of a lot more, pardon my language. And so the takeaway message from this slide is that the more bonds you have between two atoms, the more energy it's going to take to break them, right? Because more bonding means a stronger bond, right? So of course it's going to take more energy to rip them apart. Well, all the molecules that are on this slide are either monatomic, right? Like H2 or Cl2 or O2 or N2, or diatomic, right? They have two atoms, okay? So again, the monatomic molecules that we have here are H2, Cl2, Cl2, O2, and N2. The diatomic molecule that's on here is HCl. Well, there's only one way for or for hydrogen and chlorine to bond together. There's only one way for a monatomic molecule to form. But what if we wanted to look at the bond enthalpy in of the oxygen-hydrogen bond in water? Okay. Now I know this table is too small for you to see, but just give me a second here. If you had a water molecule, okay, let me just draw the Lewis structure of a water molecule. It's H2O. You get two lone pairs in the oxygen like this. Well, if you break a bond between the oxygen and the hydrogen, it costs you 502 kilojoules per mole. Then after you've broken that bond, you're left over with OH, right? You're just left over with this, okay, which would be a radical actually, but that's neither here nor there. But if you wanted to break this bond, it's going to cost you 427 kilojoules per mole. What does that tell you? That tells you that the oxygen-hydrogen bond strength varies, right? Doesn't it? Right? We see that it's different whether it's this oxygen-hydrogen bond or this one here. Since they're in different electronic environments, they have different bond enthalpies. So your question, if you want to ask a question about this, I think a good one would be, a good question to ask would be, what's the oxygen-hydrogen bond enthalpy? Well, if we take an average of those two numbers, we get 464 kilojoules. Notice that this average is reported to the ones place. Go back here. Since all these came from monatomic or diatomic molecules, they were all reported to the 10th place. That tells me that I know with greater accuracy the bond enthalpy for the bonds in monatomic or diatomic molecules. Whereas if I have an oxygen-hydrogen bond, which can be in literally Avogadro's number of different molecules, it can be in a whole holy host of different electronic environments, we have to take the average. So this, what we see here, is an average bond enthalpy. Now, if we go to that table so that you can actually see what's going on, it's a little fuzzy, but all of the molecules that are highlighted in red, these are all diatomic or monatomic molecules. And you can see that all their bond enthalpies are listed to the 10th place. They're known with greater accuracy because there's only one way in which oxygen and oxygen can bind with itself. However, if you look at all of the bonds that are listed in black, they are all reported only to the ones place. Why? Because if you just zoom in on one, for example, let's say you pick on this guy right here, a carbon-carbon triple bond, there are thousands of naturally occurring molecules that have carbon-carbon triple bonds in them, right? So this number right here, 812 kilojoules per mole, is simply an average. Well, what's the consequence of the bond enthalpy being precise to the 10th place or being an average bond enthalpy? Well, the consequence comes if we want to calculate the change in enthalpy for a reaction. So if you want to calculate the change in enthalpy for a reaction and use bond enthalpy values in order to calculate that delta H, right? Because you learned how to calculate delta H in chapter 6, right? But it was in the thermochemistry chapter. However, in chapter 6, you used heats of formation, right? You used delta HFs in order to calculate change in enthalpy. However, in chapter 9, which is where we are right now, we're going to try using delta H of, or our bond enthalpy, sorry. We're going to try to use bond enthalpy, so the amount of energy that it takes to break a bond. So I want you to think about this equation. Close your eyes maybe and imagine it for a second. But this equation is the only equation in chemistry that you ever see that is reactants minus products, right? Remember in chapter 6 when you were trying to calculate delta H, you did products minus reactants. Well, this is the only equation that is reactants minus products that you'll ever see in chemistry class. Why would it be that way? Well, let's think about it. Because when you're calculating the delta H for the overall reaction, first what you have to do is you've got to put in energy to break the bonds in the reactants, right? So that's the total energy that you're putting in, right? You got to put in enough energy to smash all the bonds. Then once the bonds are reformed to make new molecules, you make new bonds, energy gets released. And so you would subtract the bond enthalpy from the product. So this is an equation that you've got to have under your hat. Let's say, for example, and let me just come up with an example off the top of my head. Let's say you had something like a molecule AB plus another molecule that's monatomic CC, and then you end up forming AC and BC, right? When you calculate the delta H for this reaction, the delta H naught for this reaction, you're going to have to take the bond enthalpy of the AB bond plus the bond enthalpy of the CC bond, right? That's the amount of energy that you had to put in. So energy in, okay? Then what you would do is you would subtract the bond enthalpy of the AC bond plus the bond enthalpy of the BC bond, right? Because this is energy that's going to be released, so energy out when the bonds are formed. With that in mind, let's take a look at an example. Let's say you were doing this reaction over here on the left. You were taking hydrogen, combining it with chlorine to make 2 moles. Let's say 1 mole of hydrogen plus 1 mole of chlorine gas gives you 2 moles of hydrogen chloride. Well, how would you calculate the delta H for this reaction? Delta H naught for this reaction would be equal to the bond enthalpy of the hydrogen bond plus the bond enthalpy of the Cl2 bond, right? That's the total energy that you invested, right, to smash all those bonds. And then from it, you would subtract the bond enthalpy of, since there's 2 HCl's, you would put 2 times the bond enthalpy. I don't need a bracket, do I? 2 times the bond enthalpy of the HCl bond, okay? But again, these values, all these bond enthalpies are known to tenths place, right? They're all known to the first decimal place. So the delta H for the reaction that you're going to get here, let's say whatever it is, okay, is going to be more accurate than it would be for this reaction right here. Let me show you what I mean. If you were to calculate the bond enthalpy of this reaction, where you take 2 moles of H2 gas, combine it with 2 moles of O2 to give you 2 moles of H2O. I'll go a little quick here, but our delta H for our reaction would be equal to 2 times the bond enthalpy of the H2 bond plus the bond enthalpy of the O2 bond, right? Those are the bonds that we got to smash. We have to smash all of these. Look, there's 2 H2 molecules. I got to smash that bond. I got to smash that bond. There's only 1 O2 molecule. I got to smash that bond. Then once I form the 2 H2O molecules, how many OH bonds do I have? I have 1, 2, 3, 4 oxygen hydrogen bonds. So I would subtract 4 times the bond enthalpy of the oxygen hydrogen bond. However, this is an average, right? So that means that the delta H for this reaction, okay, is only going to be reported to the ones place. And this delta H over here, sorry, this delta H for this reaction will be reported to, to the tenths place, or the first decimal place, okay? So that tells me that if I compare the two, this one will be more accurate, okay? Because I only have monatomic and diatomic molecules, whereas here, since water the oxygen-hydrogen bond can be in lots of different molecules. I have to use an average bond enthalpy for the oxygen-hydrogen bond. There you go. So that's how we would use bond enthalpies to calculate the change in enthalpy of a reaction. You need to be cognizant of this formula right here. Again, remember that it's the only formula in chemistry that you see that it's reactants minus products, or at least the only one you'll see in this class. And of course, if delta H naught for the reaction is negative, it's an exothermic reaction. And if delta H naught is positive, it's an endothermic reaction. I shouldn't have to go over that again, but if delta H for the reaction is positive, you have an endothermic reaction. And if delta H naught for the reaction is negative, you've got an exothermic reaction. Well, let's take a look at a couple more problems to finish off the chapter. It says, use equation 9.3, which is the one, which is this equation right here. We're going to use that equation to compare the result that was obtained using equation 6.18, which is basically using delta HF, standard heat of formation constants, to calculate the enthalpy of the reaction process that's shown here. Well, I'm just going to do the chapter 6 bit kind of quickly here, right? Because we covered that in detail in chapter 6. So the delta H for this reaction would be equal to 2 times the delta HF of HCl. So for my HCl, subtract the delta HF, the change in the heat of formation of my H2, plus the delta HF of my Cl2. I should put brackets here to be consistent, like that. And when you do that, you get the delta H of the reaction is equal to negative 184.6 kilojoules per mole. So again, that's using the chapter 6 method. I'm not going to reteach chapter 6 tonight. But if you use equation 9.3, where we say that delta H naught for the reaction is equal to the sum of the bond enthalpies of the reactants, subtract the sum of the bond enthalpies of the products, okay? We have to break one H2 bond, we have to break one Cl2 bond, and then we form 2 HCl bonds. Well, I'm going to get the bond enthalpies from this table here, and I know it's a little fuzzy, but you see the bond enthalpy for an HCl bond, we have the bond enthalpy for an HH bond, and then we have the bond enthalpy for a Cl2 molecule. So let's plug some of those numbers in. Again, I took them all from that table. So we get that the delta H of our reaction is going to be equal to the bond enthalpy of the hydrogen, which was 436.4 plus 242.7 for the chlorine. Subtract the bond enthalpy of the products. I have 2 moles of HCl, so that's 2 times 431.9. The whole entire thing, of course, is in kilojoules per mole. And when we do that, when we punch all this spinach into our calculator, we end up with 679.1, subtract 863.8 kilojoules per mole. And we end up with a delta H naught for the reaction, which is equal to negative 184.7 kilojoules per mole. Okay? If you look at these two values, the one that used heat of formation constants from the appendix and the one we used bond enthalpies, they're almost identical in this case, right? And we could say here, results almost identical since bond enthalpies are not averages. Okay. Now, the last question that we're going to look at in the chapter involves one where we do the same kind of exercise. However, of course, when we're looking at hydrogen, we have to use the average bond enthalpy of the oxygen-hydrogen bond in water, right? And we already looked up, or we saw these values earlier on. The value for the hydrogen bond was 436.4 kilojoules per mole. For the O2 bond, it was 498.7 kilojoules per mole. However, for the oxygen-hydrogen bond, which is going to limit the number of sig figs, it's 460 kilojoules per mole. So we're only going to be able to report our answer to the ones place. Now, if you do it using the chapter 6 strategy, what you get is the delta H naught for the reaction, and I've already gone ahead and looked this up. It's negative 483.6 kilojoules per mole. So let's keep this value in mind, and we'll compare that to the heat of reaction when we use bond enthalpies. So let's give it a shot. We have the delta H naught for this reaction using bond enthalpies is going to be equal to 2 times 436.4 plus 498.7. We'll put all that in brackets. Subtract 4 times the value of the oxygen-hydrogen bond, which was 460. And of course, all of this is in kilojoules per mole. Now, in the interest of time, I'm just going to go through it here. And we get that the delta H naught of this reaction is equal to negative 469 kilojoules per mole. Okay? And so you can see that it's not exactly the same, is it? Okay? But you can see that it's very close to the value that we got when we used the standard heat of formation values. It's very close. And so this is a perfectly legitimate way of estimating the heat of reaction, right? And you're probably thinking, well, it's not that bad. It's pretty darn close, I would say. And so we can use bond enthalpy to calculate the heat of a reaction. That is a conclusion that we can draw here. We can totally use bond enthalpies to do that. It works best, we'll put here, bond enthalpies work best when the delta H of the reaction is either greater than 100 kilojoules per mole or less than 100, less than negative 100 kilojoules per mole. Anything in between, it's kind of sketchy. It's not the greatest estimate. I mean, you're going to get a decent value, but the error might be quite a bit higher than if you go beyond an endothermic reaction that's greater than 100 kilojoules per mole or lower than an exothermic reaction that is negative 100 kilojoules per mole.